All right, so we're joined here today with one of our mentors. His name is Anurag. He comes from the project Matic Network, and we're really excited to have him here today to talk about layer two scaling and some of the things that they're up to over at Matic Network. And take it away, Anurag. Looking forward to hearing what you have to share with us.
Hey, thanks, Adam. Thanks, Ankit. Yeah, so my voice is audible, right? I mean, no problem with the voice, right? Yeah, okay. Yeah, so I'm Anurag. I am co-founder and chief product officer of Matic Network. Matic Network is a layer 2 scalability solution. Right now, we're starting with Ethereum. It's based on Plasma, and we also have a proof of stake layer. So I've been involved with Bridge Academy for the first cohort. This time, not being able to spend too much time, but looking forward to do so in the future. So today, so Adam and Ankit asked me to kind of present. So I just do like a short presentation on Plasma in general and specifically how we implement it at Matic. So maybe I'll just kind of share my screen.
Yeah.
Okay. So is my screen visible now?
Yep.
Okay. Okay. Fair enough. So I'm not sure how much you guys are far down the blockchain rabbit hole, but when you kind of get into programming and you look at deploying applications, the first kind of thing that you kind of encounter is the problem of transaction throughput. In a sense, Ethereum can process like around 20 transactions per second. And so when you kind of start doing apps which need more transactions, that's a problem. So that's why when we initially started with blockchains, specifically Ethereum, we encountered this early on, and we were looking about for Plasma solutions. So we're looking out for scaling solutions, and that's how we encountered Plasma. So, but before getting into Plasma, I just wanted to kind of like throw around like a very brief explanation into why public blockchains like Ethereum don't scale, while layer one scale specifically doesn't scale, right? Because the thing is that every transaction on a public blockchain, such as Ethereum, needs to be processed by every single node in the network. So that's why you have like 10,000 nodes right now in the Ethereum network, and each transaction needs to go through it needs to go through every single node in network. It needs to have majority consensus, and so that takes a lot of time, right? In Bitcoin, that thing takes 10 minutes, and Ethereum it takes 15 seconds. So but the problem for layer one is that basically every transaction gets processed by every single node. So in terms of how you can solve that problem is maybe a naive solution might be to increase the block size, for example. But what happens in that case is then the nodes which need to support this need to be more powerful, and then that leads to the total number of nodes decreasing, and that can lead to centralization, right? And so we want to avoid that. So how layer one, and when I say layer one is Ethereum, and other blockchains. So those are optimized for decentralization and security. And if you guys have heard of the trilemma, so scaling is not optimized. For scaling, these are not optimized, and that's why we have kind of a range of scaling techniques. So there are different kind of scaling techniques that are possible, and those are on-chain, off-chain. So these are what you see on the screen. These are like the popular scaling techniques. Like so, on layer one, this could be sharding, which Ethereum is already working on. So if you've heard of ETH 2.0, so that is a combination of the transition from proof of work to proof of stake, and sharding, which is kind of like dividing the blockchain into different sections, and so then you break that problem into a manageable bit so that each node doesn't have to process all transactions. So that's one way of looking at it. So ETH 2.0, they are working on the same problem, and when that comes out, so we'll have a little bit more scalability. But even that will not be enough for the kind of future that we're talking about. If blockchain technology actually scales to what we think the potential can be, so even that's not enough. So that's where layer 2 comes in. Layer 2 is what we generally call off-chain scaling techniques, right? So these can be things like state channels. You must have heard of Truebit as well, and of course there's Plasma. So these are like the more common ways of scaling. Out of these three off-chain techniques, we primarily focus on Plasma. So I'll not get into the other techniques too much. I'll just say state channels is basically it's more like you lock one state, and then you can do a lot of processing off chain, and then you sign the states and send back and forth. So that's like example. And if you want to see a project for that, so Seller is one example, L4 is one more example. Specifically Plasma, if I come to it, it's kind of a scaling framework which utilizes side chains. This is first proposed by Vitalik Buterin and Joseph Poon in mid 2017. And so what they did is they kind of proposed a paper, and it was like, it wasn't the implementation, it was more or less like a framework. So if you will, when you kind of search about Plasma, you will not see any single project. So instead there are a lot of different implementations or projects that use the guidelines that are provided, right? So you must have heard of things like Plasma MVP, Plasma More Viable Plasma, Plasma Cash, Plasma Debit, Plasma Prime. So actually there are a lot of variants, and each of them have their own nuances. Each have their own pros and cons, different ways of kind of implementing Plasma, and kind of we will look at some of these. But essentially, when you hear of Plasma, it's a framework, and the main design consideration is that not everyone needs to process every transaction. So how I think what we will do is if you have any questions, maybe we'll just take them at the end, and I'll just take you quickly through the presentation, right? So in the sense, the basic idea that if you look at Plasma is these 5 or 6 steps, right? So I just kept it simple here. I'm just saying assets here, but this is basically you can replace the word assets by states and by any arbitrary states, right? But it's easier to visualize when you're talking about assets here. So the basic idea is what we do is we take assets from one chain or states from one chain and transfer them to another called the side chain. Now, how that is generally possible is we lock the assets up on the primary chain. So let's say in Ethereum, typically that means a contract. So let's say if you have some assets, we lock them in the contract. We ensure that the assets cannot be moved or changed. So no modification happens on the assets on one chain, which is, let's say, the primary chain, and then we transfer them to another, the side chain, for example, by creating them again. So when you're locking it up in one primary chain, or even let's say the root chain, and then you create them on the side chain. Once you're creating them on the side chain, you can actually transfer or modify state on these very cheaply, because on the side chain you're not bound by the root chain limitations of the throughput, right? And so because the throughput is high, the transfer costs are low. Now, when you want to, when you've done all your transactions or transfers or state changes, you just take the state as is, and then you send it back to the root chain. In most probably that's a Plasma contract, and then you unlock them again. So this is like the simple 5-line example of what the plasma framework is. Obviously, there are a little bit more complications, and it's not as easy just to take these assets. And I will go through them bit by bit. So this is what like a visualization of the plasma framework looks like. So here you have the root chain Ethereum, and let's say you have one ETH which is held in a root chain smart contract, and then once this is locked, it can be taken to the side chain, and these are all blocks on the plasma chain. Now what happens with part of the plasma thing is you have something called state commitments. So for every frequent interval, we take the Merkle root of the plasma blocks, the transactions happening in the plasma block, and when we commit it back to the contract on the root chain. So essentially what we are doing is we are taking a snapshot of the plasma sidechain and submitting them to root chain. This allows for in a later event, if we want to verify if a transaction happened on the plasma sidechain, we can just submit the transaction, the Merkle root, and then just verify it on the root chain itself. So in a sense, what we do is we take the security of the root chain, which is very high, and we are relying. So we borrow the security by the plasma framework. So when I say that a plasma is more like a sidechain scaling technique, there are various when you hear of sidechain, there are various other approaches, like you must have heard of POA, for example. So POA is like a normal sidechain that doesn't borrow the security of the root chain. In contrast, plasma allows you to borrow the security of the root chain to enforce transactions on the side chain. So one component is basically state commitments. So here, let's say, for example, Alice is one ETH, right? So consensus is also enforced by fraud proofs. Now, what are fraud proofs, right? And I'll come to that. But basically, these are state transition checker contracts on the root chain, right? The beauty of plasma is that, let's say, the side chain, so the block in red, for example, this is what we call a block withholding attack. So in let's say in some scenario there is an attack, the plasma side chain stops producing blocks, right? And if, let's say, some Alice, let's say, has one ETH on the side chain, with the help of something called an exit and a priority queue, any user can exit her funds off the plasma chain if the sidechain goes rogue. So even if the sidechain is not functioning as per intended, users can very quickly just mass exit from the sidechain back to the root chain, and their assets are safe. So that's kind of like the security guarantees of the plasma framework. So in kind of nutshell, what we have with plasma is you can do off-chain execution. So you're doing all transactions off-chain or on a side chain which is of the root chain. We are doing state commitments periodically from the plasma sidechain to the root chain. So what we are doing is like in Matic, we do a snapshot of the last 256 blocks, and we have 1 second blocks. So that's like almost every 5 minutes we do take a snapshot and then submit it back to the root chain contract. We have users are able to exit anytime, and then there is a priority queue of the exits. So a combination of all these 4 constitute the plasma framework. Again, I'm just explaining this in a very brief manner. There are nuances to this, but in a nutshell, that's it, right? So you take transactions on the side chain, you ensure that state commitments are happening frequently. There is a priority queue in order of states coming in out of the side chain, and you can kind of exit by way of the fraud proofs on the root contract ensure that there can't be invalid transitions. And I would encourage any of you to kind of go to the Plasma website. There's the Plasma white paper. It's slightly generic in nature, but you can kind of go to other Plasma resources for learning about specific implementations. But hopefully you got the idea, right? In terms of implementations, actually, I've already mentioned this. There are a whole host of implementations, but the most popular ones, are like Plasma MVP, which stands for minimum viable plasma. There's Plasma Cache, there's Plasma Debit, there's Plasma More VP. So More VP is more viable plasma. So it's refinement or iteration over the minimum viable plasma spec. Yeah, in terms of Plasma MVP, what we have is so there is a simple UTXO based implementation. It's primarily for payments, ETH and ERC20 transfers. Without getting too much detail, it's got the concept of confirmation signatures. So what that means is when a user makes a transaction, they will sign a first signature to have the transaction included in a block. And then just to ensure that it has been included in a valid block on the Plasma sidechain, they have to sign it again. So that's what's called a confirmation signature. The main reason for this is that if the user knows that the transaction was not included in a valid block, they would not sign. Again, this is just like a very like I'm just skimming through what's Plasma MVP. It's got a lot more detail. You can actually go to the ETH research post, which details the spec, and it's very instructive to go through the comments as well, because there are a lot of adjustments made based on the comment. Again, as a general principle, also I encourage all of you to kind of keep visiting ETH research, and it's a fantastic forum to learn about new things in the research area, right? So Plasma MVP, in a nutshell, UTXO based implementation, primarily for payments. That's what I can say. In contrast, there's something called Plasma Cache. Plasma Cache is built for so it was actually designed initially to address the mass exit problem in Plasma MVP. So in terms of Plasma MVP, when you had to exit the chain, that mechanism wasn't very efficient. So that's why Plasma Cache was built. So this uses something called sparse Merkle trees, and if you've never heard of sparse Merkle trees, I mean, you should go and check it out. It's a fantastic data structure that can you can use it in various different ways. In Plasma Cache, how it is used is, so instead of the tokens being stored in so you store the tokens or the ownership of the tokens in a sparse Merkle tree. And maybe very quickly I can show you like a visualization of the Plasma Cache sparse Merkle tree as well. So yeah, so this is kind of like sparse Merkle tree. So let's say you have like 4 tokens, right? So so all of these, each token has a slot for itself. So in Plasma Cache, you have a slot for each token. So only the slots which have valid tokens will have some information. Otherwise, they'll be empty. And so what you're seeing here is block 1, 2, 3, 4. So here, what this means is A transferred this token to B in Plasma block 1, and this is B transferred it to C in Plasma block 3. And so the beauty of this is that you don't need to monitor too many transactions. Like you don't need to monitor other transactions. You just need to monitor yours. And what this enables is that you just need to provide proof that this token wasn't included in these blocks, and it was included. And with a sparse Merkle tree, it's very easy. Again, not getting into too much detail. I know we have very short time. But the problem with Plasma Cache is primarily that it can be used only for storing and transferring NFTs. you can't do payments if you want to break them down, right? And additionally, the problem is that proofs need to be the proof that they just keep growing in size. So over a year, I don't know the exact figure, but yeah, the entire data can reach up to, let's say, like in GBs. So that's a problem. So at Matic Network, we implement what is called as Plasma More VP, more viable Plasma. It's similar in nature to Plasma MVP, but there's a significant change in that we don't have confirmation signatures that I talked about in Plasma MVP. And so because confirmation signatures is like a UX problem, because users need to sign twice for their transactions, and that's not very user friendly. So we wanted to kind of not get into that problem. So Plasma More MVP specifically eliminates confirmation signatures. It also brings in a new kind of exit priority. So that's why we implemented More VP. And again, you can kind of look at the spec as well. In terms of the Matic Network Plasma implementation, most Plasma implementations are UTXO. We chose to do it in account-based manner, chiefly because we wanted implementation with a proof of stake network, so that developers can work with both of these at the same time. So that's why we have a EVM compatible sidechain, and the developer interface is very similar. In Plasma, we have 1 second blocks. In Plasma, there is another problem called the data availability problem, where users can be griefed by the Plasma sidechain being not live or not being available. So that's why there is a proof of stake layer in Matic as well, which ensures liveliness. So in terms of, if you ask me what all is supported in Matic Network Plasma, so how we've kind of structured is that, there is the Plasma implementation, the Plasma implementation for asset transfers, for asset swaps, which basically means exchange of assets in one transaction. So in the Plasma implementation for that is complete. We are looking at doing generalized smart contracts through Plasma. That requires slightly different approach, and so we are working on those. But till the time we solve that, we also have a proof of stake layer, which is again decentralized proof of stake layer, and so the sidechain basically supports smart contracts which are secured by the POS layer. So you have smart contracts secured by the POS layer, and asset transfers and swaps secured by Plasma. So that's kind of like Matic Network Plasma in brief. This is like an overview of the Matic Plasma implementation. Again, account based, 1 second block times. So we have one side. We are starting with one side chain. It has a peak capacity of 65,000 transactions per side chain. But we are starting with a lower threshold, about 6,000 right now, going up to 10,000, and we are going to have a decentralized validator layer. This is like the rough architecture of the Matic network. So if you see, this is the sidechain, and users interact with the sidechain directly. Sidechains can have asset transfers, they can have smart contracts. We take a snapshot of the sidechain for every 256 blocks, and the validators at this layer, and this is the proof of stake layer. And these are right now 150 odd validators to start with, and this will increase in the future to about 1,000 and more. So every 256 blocks, or roughly 5 minutes, they take a snapshot of the sidechain and push it to the main chain Plasma smart contracts. And you also have fraud proofs on the main chain, which there is another concept called watcher nodes, which I'll not get into right now. But these guys keep looking at the side chain, and they can challenge any invalid transaction on the side chain. So it's like a very nice clean structure where you have sidechain security, validator proof of security, and then finally, if even if this whole mechanism goes rogue, you still have plasma exits, and you have so even if the sidechain goes rogue, everyone can exit to the main chain by way of fraud proofs. So that's how we have kind of structured it. In terms of, very quickly, I'll just to give you an idea about our adoption. And actually, I'm sorry, this is like slightly older slide, but we have more apps that are not mentioned here. But one of the main apps I would like to say is Decentraland is like a virtual reality marketplace, and they're building their marketplace on our Plasma implementation. So that basically means like, if you've not heard of Decentraland, it's like a virtual reality universe where they have virtual land, and people can build stuff on this land. So someone will build like a casino, someone build like a farm, or things like that, and actually you can actually own these. And so the land and the items in the Decentraland universe needs a marketplace to sell and buy, right? And that's where Matic Plasma is coming in, so that their marketplace is being built on our implementation, our network. We have gaming projects which are developing on us. There is a referral platform, advertising marketplace, even like a fiat wallet services provider as well. So and we are announcing more and more projects. So actually it's very easy to kind of interact with the Matic network, because first of all, we are like, so we have Plasma security for assets. We have a proof of stake layer for generic smart contracts. And so the developer interface is EVM compatible. So it's very easy to transition to Matic sidechain, and you guys should check it out. In terms of how to get started on Matic, for those developers, they want to check it out. Actually, I think you can just go to docs.matic.network, and that's like a great way of getting started. We've just kind of started doing the documentation, and we are improving the documentation as we go forward. But if you check one of these tutorials out, it's pretty simple. We have tried to be very developer friendly, and the focus of the Matic network is to be developer friendly. So you can check that out. In terms of outreach, actually, we do a lot of training programs. We go to a lot of hackathons in India and abroad. So yeah, just to give some perspective, we are primarily the dev team is primarily based in India. The team is Indian, so we present in India, but we we're like a global team as well. So the product is global, right? So hopefully, I'm not sure, Adam, what is the time, but I'm at the end of my presentation, and we can take questions if there are any.
Awesome. This is great. Thank you, Anurag, for this. Really great overview, and yeah, I definitely learned a few things here and there. So I guess we have time for a few questions from the audience here. If you guys want to pop in your questions in chat, we already have a few there that maybe Anurag you can select from, just kind of read and then can answer ones that pique your interest.
Okay. Yeah, so I'm just going through the chat. Okay. So I think the first question is most surprising types of new applications that layer 2 solutions like Matic enable that weren't previously possible. Surprising. So for example, so the thing is, what happens in so let's say Decentraland marketplace, right? So there are so many items. So let's say, like, just imagine if you were to build like, so for most people, building a virtual reality universe itself is kind of strange, right? So, but uh, I was looking at the last land auctions on Decentraland that happened, and around $6.5 million worth of land was sold on Decentraland. And even though we are very closely related, so that was like a surprising fact, right? Like people are actually investing in these virtual pieces of land, right? And if you now think of what do people build on this land, what will people build on this land, right? So it can be anything. It is up to the human spirit to kind of envision and build it. Now, in terms of if you see actual economy developing on Decentraland in the future, probably you will have a lot of things being bought and sold, right? And there could be like innovative economic models developing on Decentraland, right? And that's just one example. So those kind of things which we haven't seen in the real world, which may be possible in when we take something like like say a virtual universe, combine it with crypto economics and I don't know, behavioral economics, I don't know, new kind of economic application. So maybe, yeah, probably that's my answer.
Nice.
Okay.
And because on Ethereum, because you're limited by the kind of transaction throughput, so developers also kind of put like they don't, they like to put a tab on what they want to do. So if you don't constrain them, you'll get many new surprising applications. So hopefully that is the answer to that.
Great.
What type of applications have no one built using Matic Dagger that you would like to see built? So that's an interesting question. So actually, so there have been a lot of applications built on Dagger, but there is always potential to do more, right? So there is always, so things like I've seen a maker scan. I've seen like things like monitoring of DAI contracts, monitoring of maker contracts, monitoring of Dharma contracts, but so we have soon we are kind of going to announce a couple of partnerships for Dagger, but specifically I would say DAO, decentralized autonomous organizations. That's like a very interesting concept, and if you can imagine like an organization being built with these, let's say like an Aragon DAO, right? And just imagine the daily functioning of the organization, and you need to have notifications in that case. So Dagger enables, for those of you who don't know, Dagger enables real-time event notifications for Ethereum. So something like that would be dope.
It's like a real-time shareholder report or something.
Yeah, something like that.
I like that.
Yes. A game, for example, let's say some. So you could have like a text twitch for a game, for example. Anything is happening on a game, you use Dagger to kind of report. So I mean, there can be a lot of applications. Okay. Do you believe that most protocols need to dog food? Yeah, it's my personal opinion is you always need some dog fooding. So the community, the community we need to engage with the community to build more apps. But I think dog fooding is a big part. So we also plan to bring up a few products ourselves, and then we also we are partnering with developers. Yeah, actually, I wanted to point one thing out is we also released like a developer support program, which is like a $500,000 program, which will support developers developing on Matic and Ethereum as well. So it's not a only program. So yeah.
Nice. Where can people find that? Where is that?
Yeah, maybe I'll kind of share a link to that with you guys, and
that would be great.
Yeah, I'll share the link.
Perfect.
Great.
Okay.
We got time for maybe one or two more questions. Ankit, you want to ask yours?
Yeah. So the third question has sort of already been answered. My primary concern is the fourth question. What is the advantage of using Plasma versus state channels? There are a lot of use cases for state channels merging now. I guess like Cent is using state channels at this point of time. DC is using plasma. So like where so if I am building a D app at this point in time, uh, what points should I take in consideration versus while choosing between plasma and state channels?
Sure, sure. So see, basically, I think from a developer's point of view, the most important thing is couple of things. One is that the developer interface. How do you kind of interact with these networks, right? So that's what I think like the primary thing. The second thing is also in terms of when you're the security of these off-chain scaling solutions. So I would say on the second point, plasma chains and state channels are kind of secure, right? They score evenly. In terms of developer experience, I think plasma sidechains are much more better. So if I were to kind of just single out one point, that would be that. In Matic, we have actually taken special care to make the APIs EVM compatible. On state channels, that's not a very it's not very easy to do. A third thing is also that when you are talking about generic state channels, right, like which can handle any state, in that case, what happens in state channels is when there is a problem in the off-chain, like if you're doing some let's say two-way or multi-party state channels, if there is a problem or if there is a conflict, how do you solve that? So you need to then basically deploy the logic of that particular state transition on back to the root chain and then kind of verify. So again, it comes back again to how is the developer experience. Okay. So that's kind of my answer. Yeah.
Okay. Cool.
That's it. So I think, guys, that's all the time we have today for questions. But I hope you found this as educational as I did. So I wanted to thank you again, Anurag, for joining us. This was great.
Yeah. Thanks, Adam. Thanks, Ankit, and thank you everybody for listening in.
Awesome. All right. Take care. Thanks.
Thank you. Bye.